Thank you for coming. I'm going to introduce you a new technique for designing arrays, but in a different way, in order to enhance the broadband response. So I'm going to show you which is the objectives of our new kind of fabrication method, and the description of the system, the method we are using to assess all the characteristics, and then the measurements and the conclusions. So typically, a typical approach to design a piezoelectric transducer is to rely on geometric resonances, typically in the thickness mode, in order to achieve a better signal to noise ratio. So this thickness mode provides you with a lot of gain in one specific frequency, but usually you have to manage a trade-off between this sensibility and this bandwidth. No? As long as you have a high sensibility, you will have a lower bandwidth, and so on. So usually arrays are designed to get this thing, both things, so both worlds accomplished. Sorry. Okay. So our final goal is to enhance the most in a wide way, the most we can with our fabrication. So why we need this broadband response of the system? Usually broadband means more temporal resolution or more spatial resolution, and in terms of medical imaging, it's quite nice to have this. Also, we can provide a more different responses or broader response in cases of non-destructive testing. So we have a broad spectral response. That means that we can measure different sizes and more things. And then in ultrasonic communications, if you want to transfer information, the more band you have, the more data you can chunk in, and the more codification you can add, encryption. So it's kind of a limit when you're designing this kind of systems. So with this in mind, our target was to have the widest band response. We would like to design an array which have overlapping bands of frequency, and we were choosing a annular geometry with two elements array with an outer ring and an inner disk, but we're using a mechanization process. We start with a ceramic, and instead of creating elements by like the kerfling technology, we're using a composite which has a very low crosstalk between elements. So we mechanize this. In this case, we're using a 1.3 PCT 5A composite, and then we add a different kinds of passive components to enhance furthermore this broadband response. In this case, we have a lambda fourth quarter wave length filter in the beginning, a matching layer. I'm sorry, and usually we add as well a backing layer in order to reduce these echoes that we don't want inside our signals. So this is the design. So this is the ceramic, and we perform just a drill in the center. We encase it with an aluminum casing. We place electrodes in both surfaces, and we add a matching layer to reduce the mismatch with air or water in the case of this design. So we use these devices in order to make our measurements and all the things. So we have a network vector analyzer to have impedance measurements of the transducer. Also, we have a pulsar to get this working with a parametrics pulsar, and we are using pulse echo signal conditioning. So we have a negative pulse. And then we measure the signal back with an oscilloscope, and MATLAB is used to process this. And we have some measurements made for the field that we used a water tank with the transducer immersed, and with a needle hydrophone, we made some precision acoustics of the field, the near field. And this is also controlled by a CNC machine, so we can have precision in space and in the measurements. So this is an outline of the fabrication process. We start assessing the ceramics when we buy it. We make a mechanical measurement on an acoustic, an impedance measurement of the original disc. Then we go through the machining process that make a drilling, and then we assemble it with the casing, with the electrodes, and then we add the matching layers, and then we do all the rest of test. So here, this is, you can see the original disc is this size, 6 millimeters and 25 millimeters diameter, and we have the typical impedance resonance in a mechanical of a ceramic composite. So we here see the radial modes that are quite damped because of this the arrangement of the fibers in this composite, and we see the thickness mode that is the one we are exploiting. In this case, this arrangement, this geometrical arrangement, gives a resonant frequency of 250 kilohertz. So this next step is we make a drill, and as you can see, the drill is done, but our response is almost the same. We are keeping the resonance of the system in the way it was in the beginning, and keep in mind that we are pulsing with the outer range, with the outer area. So now we are using just that part because we have one electrode in the top layer. So we are really pulsing with just the outside of the system, and we get this response. Then if we measure the inner part, you can see that now the part that is pulsing is this one, and you can see that there is another resonance added to almost twice the frequency that was made, because now we have this region pulsing in one frequency because of the geometry, and we have the outer region pulsing in another frequency. So we're getting two signals, and we are going through these overlapping bands that we are looking for. So in the next phase is to have these matching layers. So we're using this equation. We want to match the impedance of the water, so we design two different layers because we have two different resonant frequencies for the two regions of the transducers. So in order to get these two different layers, we're using two different materials. One layer is made with an epoxy and an alumina addition. Then we get this speed of propagation of sound. And then the other outer disc is using urethane with some wolfram addings, and we get another speed in order to get because we want the same thickness in both layers in order to have a radiant surface that is almost flat. So when we add a layer, first measuring the outer part, we have the lambda 4 layer add-on. So we can here see the typical 2 peaks by 1 because of the matching. Now it's more matched, so we are covering an even more band. Then if we see the outer part, we can see as well that there is 2 peaks there. So if we see all of them together, we can see that in the beginning we have this resonance, and now we have much more band. So we're covering, we're reaching our target. So this is the device. Only one cable is pictured because we have 2 terminals in the back. So you can see more or less this is the matching layer, what you are seeing. You're not seeing the ceramics, but inside you have the ceramic disc with the drilling, the electrodes, and this is an aluminum casing. So then we go to making some field measurements in this water tank that I mentioned earlier. And here you can see, first we made a measurement using just the outer ring for pulsing, and this was the actual measurement on the tank. And this one here, it's a simulation made just to try to recreate what will happen. And you can see it's striking the resemblance between the simulation and the actual measurements. We do the same. I mean, this is the in focus. We meet more or less where the more energy is placed. We make a measurement of the temporal signal and also the bandwidth. And you can see here the peak of the mechanical resonance and the electric impedance resonance of the outer ring. This is the second harmonic. So we do the same for the inner disk, and you can see same our field, the temporal signal, and our peak of our resonance where it's expected to be. So if we add those together, there are some errors in the alignment, and this is not quite in shape. But you can see that we have an overlapping field that it's quite long. I mean, this is, I don't know. These are around 30 centimeters, something like that. So once we start adding these bandwidths together in order to see what it looks like, we have this is the inner disk, the red one, center there. We have the outer ring with the initial resonance, and then the second order, and the black one is the sum of all the bandwidth on the overlapping bands of the two elements. In this case, we're using one pulsar in the red one. It means we are using the same setting to exciting both elements of the array, so we get not so flat response from the system. But when we equalize this exciting signal, we can get a much more flatter and much more near what we wanted to get. So as a final conclusion, you can see a comparison with a typical transducer of a 0.25 megahertz resonant frequency, and this is the transducer we get in the end, just performing one drill on one composite. So in the end, we get the bandwidth that we are looking for, because you can see the band comes from almost 200 kilohertz from 1 megahertz. So our target was achieved, and the bandwidth was extended. So thank you very much. Any questions? Yeah, the crosstalk was very low, because the composite we're using is like columns of fibers that are embedded in an epoxy matrix. So the crosstalk between elements is very low because of this epoxy matrix. So really, the thickness mode is the only one enhanced. So you can just see this mode of operation in the system.